Back when I was a student in college, 1977 through about 1982, biology students used to spend quite a bit of time learning how to use keys. Now, I don't mean the kind of keys that you open doors with. Well, we had keys back then, but this kind of key is a series of questions, kind of like 20 questions, that when you answer them all, I guess, correctly, what you wind up with is the name of the species of plant or animal or whatever you're looking at. And keys are still used to identify living things, to get them down to family or order, genus, species, whatever. But it's not something maybe that is emphasized as much at the undergraduate level as it was 40 or more years ago. So anyway, we're going to be using a couple of keys here in this video. And key characteristics, therefore, are the characteristics of the mussels that we're going to be looking at that we'll use in the key or keys to figure out who's who. I started doing mussels in about 1994 and didn't know what I was doing, but I got my permit from the state, and I bought myself a book and headed out there into the wilds of Fort Wayne to try to figure out who is who and what was what. And the book that I used and still use is one by Kevin Cummings and Christine Mayer. It was published in 1992 by the Illinois Natural History Survey. It's called The Field Guide to Freshwater Mussels of the Midwest, and it's still in print. And all of the particulars on these three references appear at the end of this video if you want to look them up, or maybe purchase a copy one for yourself. This first one, Cummings and Mayer, I particularly like because it's concise, it's small, it'll fit in your back pocket. It's well, it's illustrated. It has just enough in it, and it covers the region that I live in. Of course, the Midwest. Indiana's in the Midwest. So that's a really good one, and that one really got me started. And of course, all of these have their pros and cons. There's some drawbacks to each. One of the things I wish was in Cummings and Mayer were illustrations of the inside of the shells. Shows the mussels from the outside really well, but you can't see what's going on with the teeth and all that. That we'll see here in a little bit. It can be kind of important. I remember being really excited and happy when Parmalee and Bogan published their book about freshwater mussels called The Freshwater Mussels of Tennessee in 1998. One of the things I really like about that is it had and has synonymies for each of the species. So, one of the things that we're told when we're young and impressionable young biologists in college is that we use scientific names because they're universal, they're used all over the world, and the impression that's given is they're pretty stable. And in some cases, I suppose, some groups of plants and animals, that's relatively true. It's decidedly not true when it comes to unionid mussels. There's dozens, sometimes 50, 100 different synonyms, of Latin names that have been used over the years for the same species. And oddly enough, the common names are more stable through the years than the scientific names are. But anyway, so Parmalee and Bogan provided me with kind of Rosetta Stone of names that have been used in older literature, so I could do some translations, if you will. An example of that would be Pyganodon grandis, which is one of the species that we have here at Crooked Lake. And in Cummings and Mayer, that species is called Anodonta grandis, but the genus changed on us, and now it's called Pyganodon. So, you know, a synonymy can give you those kinds of bits of information that can be very helpful. And the most recent of the three, of course, is this one by Tom Waters, Michael Hogarth, and David Stansberry, came out in 2009, and it's called The Freshwater Mussels of Ohio, so our neighboring state just to the east. And it also has synonymy, good descriptions, excellent illustrations, so it's very helpful as well. Now, as we look at these species here in the following slides, I want you to realize that I'm basing my key characteristics on what I think is important, what I think helps to distinguish the 6 species one from another here at Crooked Lake, and I'm using the information in those 3 references as well as my own judgment and experience to try to help you in figuring out differences between them. And as we look at these characteristics, also be aware that the ones that are in the typefaces in blue, I think those are particularly helpful in discriminating between species here at Crooked Lake. All right, so let's dive right in this, shall we? Let's start off with the species that I've done most of my work with here at Crooked Lake, Lampsilis siliquoidea. And part of the reason that I've focused on this species is because in the mussel bed it is it has been quite plentiful. It's every time we've looked at the mussels down there, it's always been the most common, the most plentiful of all of the species. Now up here you'll see it says male in quotes, male morph. What do I mean by that? The literature indicates that this species, as well as several others of this related group, are sexually dimorphic. So in other words, one is able to tell, supposedly, genders, male and female, based upon external shell characteristics. Now, of course, if the animal is in breeding season, as it were, it is possible, it would be possible to open it up, dig in there, find the testis of the ovaries, put some of that tissue under a microscope and definitively tell whether it's male or female based upon whether you're seeing sperm or egg. And by the way, the unionid mussels, not exclusively, but in general, have separate sexes. There are some species that have that are hermaphroditic, and some may even change sex. But for the most part, most species of unionid mussels start off life as male, finish life as male, start off life as female, finish life as female. Well, anyway, supposedly one can tell a male siliquoidea from a female siliquoidea simply by looking at the outside of the shell without having to do anything else. I'm not quite as convinced about that as I used to be, and maybe that's the subject of a later episode of this series. But for now, let's just call it sort of male in quotes. This is what a male siliquoidea may in fact may look like. And here in a little bit we'll look at a female morph. So here are some key characteristics. There's a whole big long list of them, and I've tried to keep these consistent from one species to the next in order and which characteristic goes with which little with letter A over here or B or whatever. So A refers to something called the pseudocardinal teeth, and these top 4 key characteristics are all things that you have to look on the inside of the critter to visualize them. So consequently, you know, if you have a live mussel in your hand and you're trying to figure out what species it is, those top 4 A through D key characteristics aren't very helpful unless you happen to have an X-ray machine or some other fancy gizmo at your disposal. Like I said before, the stuff in blue is, in my opinion, pretty helpful in trying to discriminate species out here at Crooked Lake. The things in black aren't all that useful, or I haven't found them to be all that useful, and I'm including them here just for the sake of completeness, but we're not going to focus on those items. What I will do, though, is walk you through A through M here on this first slide, and that way you can get a little bit of anatomy, you can get a little bit of background, so it'll make the rest of them go quicker. So we'll kind of grind through this one after the next, and you won't have to do it for all the species, okay? All right, so let's hit this this A first of all. Pseudocardinal teeth. What do I mean by that? Well, in marine bivalves, and in some of the older literature that you'll see surrounding the freshwater bivalves, you'll see these referred to as cardinal teeth. And evidently, some academic decided a long time ago that these teeth I'm going to show you aren't real real cardinal teeth. They're fake cardinal teeth. They're pseudocardinal teeth. Whatever. Okay, so where are they? Let's see here. So if we look down here, you can see just right there a little protrusion. Yeah, right about like that. That's looks like a tooth. In some cases, not this species, but in some cases they look like molars. They're big, they're heavy. In others, like this one, maybe a canine or an incisor, they're not real teeth, okay? They don't chew their food with these things. They just kind of look like teeth. So that's where the pseudocardinal teeth are located, and what they do is they help to hold the shells relative to one another, so they don't move when they open and close a little bit. They're a little bit like a hinge, or the parts around a hinge that keep everything lined up. Okay, so that's the pseudocardinal teeth, and in this case, in Lampsilis siliquoidea, they're relatively small, and they stick up. So they're kind of like incisors or canines, if you want to use that terminology. All right, so B, the lateral teeth, are located here. So there's the lateral teeth. They're long and thin. And in this case, looks like there's 2 of them. So on the other side, on the other valve of the shell, there would be another lateral tooth that would fit in between those 2. And again, this helps to stabilize the shells so they don't move relative to one another when they're opening and closing, or when they're experiencing some kind of mechanical stress. And here in Lampsilis siliquoidea, it does appear to be, those teeth appear to be slightly curved. They're not exactly straight, if you laid a ruler on there, you'd see they curve a little bit, and they're pretty thin. The nacre of the shell is this shiny stuff on the inside, all of this kind of whitish, bluish white material is the nacre. And in this species and many others, it's we're going to call that white. So all that stuff, you have to open up the shell to see what's going on inside, A through D. E through M is visible from the exterior. So we're going to start here with the umbo and work our way down. So the umbo is this spot right here. Looks like a little bump. And when you look, when you flip the valve over, there's the umbo again right there. And in the case of siliquoidea, the umbo is elevated dorsally and anteriorly from the hinge line. So, this is the hinge line here. There's the umbo there sticking up. So that's what we mean by elevated above the hinge line. Now the umbo is where the animal starts out. So you're kind of looking at the history of this critter. So when it was a baby, it was just maybe that big, and in many cases the exterior material gets worn away. So this is a case where we can actually see the material, the periostracum, is still intact, even though this critter is several years old. It hasn't eroded away yet. In many cases, that's not happened. The periostracum, the covering, is worn away, and that area is just white and eroded. It is possible to see textures. When you get in there with a magnifying glass and you look at that umbo very carefully, you can see what's called umbo sculpture. And folks in museums, taxonomists and so on, use umbo sculpture as a way of identifying species. And I've got it here in black because it's not something that we typically use here at Crooked Lake to distinguish between species, in part because of that issue of it eroding away. So in many cases, it's not present, so you can't really see it. So we're not going to worry about that at the present time. At least you know where the umbo is, and that there is sometimes there's patterns that can be useful in identifying species. Now, pustules, on the other hand, usually if they're present, they're present in full-on adults, and it's pretty easy to see them, and they don't usually get worn away. And pustules occur all over the exterior of the adult shell. I'm not seeing any here in this specimen, or actually in any of the specimens that we have at Crooked Lake. Now, if we were working in, let's say, the St. Joe River in Allen County with those mussels, a lot of those do have pustules that are helpful in distinguishing one species from another. So that's one of the reasons that I put it in black here, because none of the species here at Crooked Lake have pustules. Therefore, it's not helpful in discriminating between them. All right, so ridges, H. I'll show you what ridges aren't. Ridges aren't these concentric lines here. So those are growth rings. So at the times when the animal is growing really slowly, maybe in times of stress or the winter or whatever, you get these lines here, and folks use those sometimes to try to figure out how old a mussel or a bivalve is. those external concentric, what are called annuli, are not ridges. Okay, ridges originate around the umbo and radiate out toward the edge. So here's another thing that's not a ridge, okay? See this line right here? It's kind of a dark brownish line. There's one there, there's another one there, there's another one there. They're kind of radiating out from the umbo, aren't they? So isn't that a ridge? No, those are rays. Rays are just colors, like paint, right? But they're not, you can't feel them with your finger. You know, if you have your eyes closed, you can't tell where one ray leaves off and the rest of the color of the shell begins. I guess some are really sensitive to things like that, but most people wouldn't be able to do that just by feel. So those are rays. Those are not ridges. But I mean, doesn't H say that there's a modest posterior dorsal ridge on this critter? Well, yeah, there is. And here it is right here. Start up here at the umbo, and that ridge, the edge of the ridge runs right about there. Okay. So I'll take away that red line so you can once again see where that ridge is located. If you had the three-dimensional shell, the real object in your hand, you would be able to get in there and feel where the texture changes. There's actually a little ridge, like the ridge on a mountain, that runs from the umbo posteriorly. Okay, so there it is again. Now, why do we call it the posterior dorsal ridge? I mean, there's other locations for ridges in different species of mussels, but we call it the posterior dorsal ridge for the following reasons. I'll explain that here by showing you where dorsal, ventral, and all that jazz is. Okay. So here's where you get your little lesson in shell orienteering. So you'll know when we're done with this little bit what's up, down, front, and back. Okay. So this shell that we're looking at here, this valve on top, is the left valve of a mussel. And the umbo, as we've seen, the umbo's right there. There's the umbo. The umbo, when you orient that up, as we have in this figure, that means that this top part here, this top edge, is dorsal. That's kind of like the back of the mussel. And this down here is ventral, so the bottom, like the belly. If this was a cat or a dog, you know, you pet the back of the cat, and then sometimes, you know, the cat will roll over or the dog will roll over, and you can pet its belly. That's its ventral side. The ventral is the bottom. Okay. And then the umbo points toward the front. So the front, in biology speak, is anterior. So that's up here. So that's the front end, anterior. The back end, the trailing edge, you might say, is the posterior, and that's back here. Okay. So we've got dorsal's the top, ventral's the bottom, anterior is the front, and posterior is bringing up the rear. So that's why we call this here the dorsal, or the posterior dorsal ridge, is because it's located sort of toward the back and the top. All right, so what about this profile shape business? we have to do a little bit of measuring here to figure this out. When we look at the shell length, basically we're putting our calipers on the front end and we're measuring the longest distance between the front and the back. So that's the shell length, and then we try to visualize a perpendicular line that gives us the greatest distance perpendicular to the shell length. That's the shell height. And those two numbers divided one into the other gives us a ratio that might be, in this case, somewhere between 0.5 and 0.6, thereabouts. And that gives us a notion of how sort of high relative to long the critter is. And I've established, or I've defined for the purposes of this key, 3 different shapes: oblong, elliptical, and elongated, that fall into ranges. So that's what these numbers are here. They tell us that we're looking at a shell that's between 0.506 and 0.600. That's what I've called elliptical. For this particular species, for siliquoidea, for the male morph, shell height divided by shell length runs between these two numbers here. So it's a little tighter than just saying elliptical. This defines the range for that male morph. The periostracum is what you see on the outside of the shell. That's all this brownish stuff that's covering the outside. It's a protein layer that covers the outside, helps to protect the animal from abrasion, from being dissolved away, because calcium carbonate is, of course, soluble in fresh water. So that periostracum helps the animal to maintain the integrity of the shell. So it's visible on the outside. And it has some limited utility in telling species apart, although it does vary depending upon genetics and diet and a lot of other factors. So again, here's those rays that I talked about, those brown rays in this case. We're seeing those. Those are part of the periostracum. So they're a color within that protein layer. And I don't think it's terribly important in distinguishing species here at Crooked Lake. So you'll remember from a while ago, this is like a little quiz, that the posterior is back here, anterior is up here, right? So when I'm talking about this letter L, this posterior point, that's this area right here. That's what I mean by the posterior point. And I gotta say, I didn't get this out of the literature or any of those 3 references. This is something that I just came up with myself. But I do think it's kind of helpful in field identification. When I look at just the overall shape of the shell and what that point is doing, what I see is kind of like an arrow that points this way. And to me, that looks like it points straight backwards, not up, not down, just more or less pointing toward where the animal's bend, right? If it was moving toward the anterior end. So I'm saying on this species, for this morph, the posterior end points straight backward. Oh my gosh, here we are at M. Bet you thought you'd never make it this far. Maybe you didn't. Maybe you quit watching a long time ago. I don't know. Anyway, the ventral margin, that's, ventral, as we said, is down here. And the margin is the edge of the shell. So I'm talking about this right here. That is the ventral margin. And on siliquoidea, that ventral margin is either straight as a die or just a little bit concave. Okay. So it kind of looks like it's pushed in just a little bit relative to these other ends. That's what I mean by concave. Okay. And this is the same shell, of course, flipped over, the same valve, and yeah, that looks a little bit concave. I kind of exaggerated it there a little bit. Woo! So finally, we get to move on to a new slide. Ooh, exciting. And this one is, but it's still siliquoidea. This one is, in quotes, the female morph. And we'll be able to whip through this pretty quickly. The pseudocardinal teeth, same as the male morph, small and erect, lateral teeth. So, yep, slightly curved and thin, white nacre. The shell is, I guess I skipped that earlier, didn't I? The shell thickness, it's pretty strong. I mean, you can handle these guys without worrying about them cracking or breaking up on you. That's not the case with some other species of mussels. You know, when you've got them in the museum, actually sometimes some species will just spontaneously crack because of changes in temperature and humidity once they're in the drawers for a while. That's not the case with siliquoidea. They're pretty robust, pretty resilient. And again, you know, the umbo still elevated past the hinge line, double loop sculpture, doesn't have any pustules, has that modest posterior dorsal ridge. Here's a difference though. The profile shape is quite a bit different from the male. It's quite swollen in the posterior area, and it's thought that that is an adaptation to brooding Glaucidia in the gills. So that's where the gills are located, and those get filled with little baby mussels when she's pregnant, and the shell is bigger in that area to accommodate that material. Another difference from the male morph is the posterior end. So when I look at the overall shape of the shell, it looks to me like the posterior end is pointing up rather than directly backwards. And part of that is just because of that swelling in that posterior end that kind of changes the shape of the overall shell. It kind of looks sort of triangular in a way as well. It's like looking at constellations, right? You look up at Cassiopeia, and it's like, I don't know, it looks like a W to me, but just to ancient people, it looked like something else, I guess. And like the male, this ventral edge is either straight or just slightly concave. And we're going to temporarily stop there. It's been almost a half hour, and I don't want to try your patience. There's another half hour of material to go, so we'll pick that up in episode 8, so you can look forward to that next time. Take care. Bye.